Hello, can you hear me? Good morning, everyone. Okay. Hopefully you had some coffee and feel better. Okay.
Hold on a second, let me introduce you. This is Alice Fu, and I have a bio here. It's very short.
Like me, right? Short and sweet.
She works in the biogas analysis with online gas chromatographs, or that's where her presentation is going to be. Our company is Emerson. Can you guys hear me? Okay. Is Emerson Automation. She's a senior global production manager. And her education is a Bachelor of Biomedical from, I'll let you pronounce that.
Yeah, those are the colleges in China from Zhejiang University and MBA from Shanghai Jiao Tong University.
Okay, she has 5 years experience in telecommunication, 21 years in automation with Emerson, customer 2 years plus for application support, and 15 years plus in. And I'm assuming all of this is concurrent, not added on top of each other because you're too young to be that old.
Oh, thanks. I started as a child labor.
Okay, so I think you guys are in for a treat.
Okay.
Thank you so much.
Thank you, Wes. Good morning, everyone. Thanks to ATC for giving me the opportunity to speak, to talk about biogas and RNG analysis with GC. I really like ATC, not that you can see all the latest, greatest analyzer technologies. Also, I see a lot of my old friends. So if some of you are here today, thank you for coming. You might be wondering, what is Miss FU going to talk about today? Just wait and see, okay? Okay. Here, okay. Yep. So we are going to talk about why are we talking about biogas? How do we produce biomethane from biogas? And what are the key analysis points and the measurement requirement? Then I will share a few examples of how to use GC to measure biogas. So first, let's get on the same page with a few terms that are commonly used. So biogas really includes raw gas and biomethane, which is a product. So the raw gas is produced by bacteria through an anaerobic digestion process. So it is raw. It does not meet the pipeline quality. So raw gas is dirty. The primary composition is methane. And it also includes CO2, moisture, oxygen, nitrogen, and usually high H2S. So the biomethane is a product from the biogas, raw gas, after it's been cleaned and upgraded. And in North America, it's commonly called renewable natural gas, or RNG. So these two words are going to be interchangeably used for this paper. So also, the biomethane is also called a biogas product or outlet or sales gas. But when we talk about biogas, have to think, are we talking about the raw gas or the product? So then there's another set of concepts, natural gas and RNG, NG and RNG. What are the differences? So they have almost identical composition, mostly methane, right, and some impurities. But traditional natural gas, we all know it's a fossil-based fuel, right? So the RNG is produced through those renewable organic waste. So really the difference are the sources. The reason that traditional natural gas is considered non-renewable is we know that it takes millions of years for those fossils to form. But the rate that it is being consumed by humans far exceeds the rate that it forms. So that's why it's considered as non-renewable. But for the renewable natural gas, because the sources used to produce it are just organic waste, as we all know, as long as life exists, we continue to produce waste. Just go check out the bathroom during the break, right? So, so now let's see, how do we produce biomethane from biogas? So this diagram shows a very typical process. So we can collect all sorts of organic waste, including agricultural waste, animal waste, wastewater, all sorts of household or industrial waste, like food waste, etc. So we collect all these waste. We feed into a sealed vessel. It's usually called anaerobic digester or reactor, where those bacteria start working to break down those waste. And then biogas is produced. So the biogas can be cleaned, upgraded to produce biomethane, and biomethane can be used interchangeably with conventional natural gas as fuel, or you get fed into the gas grid to use as fuel for the homes and industries. The other byproduct from this process is the other digestate. It can be liquid or solid. After being treated, it can be reused as fertilizer or soil amendment or livestock beddings. So this is a typical process that how biomethane is produced. So we talked about, from biogas to biomethane, it has to be clean or purified or upgraded. So the aim, of course, is to remove the unwanted, including those components that does not contribute to the heating value, right? As a fuel, you have to have heating value. Also, remove those components that can pose risk to human, to equipment, or to the environment, such as CO2 or H2S. So the technology that are commonly used to upgrade the biogas, there are 4 types. Membrane separation, pressure swing adsorption, ambient scrubbing, or water bath. So it really depends on what type of biogas you are dealing with and what level of purity you try to achieve and the cost, etc., right? So all these technologies, the purpose is to achieve high product quality. We want the methane as pure as possible. Also, to meet the EPA renewable fuel standards, right? So during this process, from biogas to biomethane, there are 2 key measurement points. One is right after the digestion process, measuring raw gas, because the composition of the raw gas directly affects its product quality, so it must be measured. Also, you want to know what's the H2S level, because you do not want your equipment to get damaged and pose risk to human and environment. The other measurement point is at the product side, before the biomethane being injected into the natural gas grid. Of course, we have to ensure that the product meets the pipeline quality specification before injected. So GC can be used at those both key points. So now let's look at gas chromatograph, this technology. Yesterday, we already heard about it. Gas chromatograph is a very mature, established technology. So chromatograph, this word is actually a Greek word, means color writing. You might remember this experiment that we did in the middle school in the chemistry class, and you can do it at home to show your kids, right? You bring a bottle of black ink, and you dip a piece of very absorbent paper into it, and you wait for a few minutes. You notice that the different color bands form on the paper. So those different color bands are from the pigment from the black ink. So this experiment vividly shows that a group of compounds, when they travel through a media, the different components in that compound can be separated depending on how fast they travel through the media. So chromatograph works off the same principle, separation and detection. But of course, chromatograph is much more sophisticated compared with that bottle of ink experiment. So here I'm showing a very simple, basic chromatograph system. So it has 3 parts from the left to the right. On the left, it's a simple conditioning system. Its function is to extract a representative sample from a process and then condition it. Conditioning means that it filters out the unwanted particles or the liquid mist, and adjust the pressure and the flow rate of the sample to meet the requirement of the analyzer. Most gas analyzers love clean, dry sample, right? And also bypass the sample that's not injected. And then the sample will be injected into the oven. That's the one in the middle. Oven is where the magic happens, right? Oven is heated to make sure to keep the sample in single vapor phase. And it includes 3 key analytical components. One is the analytical valve. Its function is to inject the sample, direct them to different columns. Column is a long piece of stainless steel tubing packed with very fine grain. Usually they are polymers or sometimes glass beads or other material. So column is where the separation happens. When the sample goes through the column, the different components, some run faster than the other ones, just like running a marathon, right? First, they all come together, leave together, but then the faster ones lead, and some people are just lagging behind. So after the components are completely, totally separated, they elute through the detector one by one. So then the concentration of each component is determined there. So all these information get fed into the controller, which is on the right side of the diagram. So there all the data are being processed, reports are being created, and all these analysis reports, chromatograph can be sent to your flow computer or SCADA system, DCS, or other type of control systems. And also the controller controls the operation of the GC. So if we compare a chromatograph system with a human body, basically the sample system is like our circulation system, right? And the oven is the heart. And then the controller is the brain. So all these parts work together as a system, provide measurement. So GC technology is the most implemented technology in the natural gas custody transfer and generally in oil and gas industry. GC provides comprehensive composition analysis. With that information, we can determine the product quality, the impurities, and the heating values, BTU. And also with the composition information, so all sorts of physical properties can be calculated, such as specific gravity, compressibility, Warby index, hydrocarbon dew point, etc. The reason that GC is so commonly used is because it is very, very accurate. It physically separates the components in a sample. There's no interference. We can zoom in on individual components. It is very versatile. Depending on what type of detectors you are using, GC can measure all sorts of hydrocarbons and non-hydrocarbons, like all sorts of inert gases and impurities like sulfurs, a lot of components. And also GCs are usually designed for using in harsh environment. A lot of GCs are suitable to be installed outdoor and work for many, many years. Like 15 years is very common, right? So, due to the similarity between the biogas and the traditional natural gas measurement, GC technology is being widely adopted in the biogas industry. So I'm going to share 2 examples to show how GC can be used for biogas measurement. So we talked about raw gas and a product. And I'm going to show the first example is how to use a GC to measure biogas, raw gas. So on this slide, on the left side is a stream composition of the application example. So you can see on the top, it's the stream name, the process condition, it tells the pressure, temperature at the sample point, the sample phase, and the distance from the sample tab to your analyzer. And then it lists out all the components in the sample and their concentration, and also tells you which components are being measured and what are the measured range. So for example, in the raw gas, of course, we want to measure methane. So this one, the measurement range is 0 to 100%. The other critical components is H2S, because in the raw gas, there's usually high level of H2S. They vary depending on the feedstock you use to produce the raw gas and also the process you use. But it's very common, the H2S can range from 100 ppm to 2%. So let's look at our solution using GC to measure this gas, okay? So a model 470XA is being used, and there's one sample stream and one calibration stream. And diaphragm valves are being used as analytical valves. Carrier gas or other inert gas can be used to actuate the valve. The stream switching is automatic with internal single block and bleed configurations. The column used as 1/16" macro-packed column. And the cycle time for one stream measurement is about 5 minutes per stream. So you can have multiple stream if you need. You can stream switch because EPA requires you give an update every 50 minutes, right? So the BTU will be calculated. And for this application, helium is used as carrier. If you want to use hydrogen, that's okay as well. So the system power is 24 VDC. So now, let's look at the measurement result. So on the left side, it's a chromatogram, right? So the chromatogram, there are multiple peaks. Each peak represents one measured component. And to identify which peak is for which component, you look at the little table on the right hand, low right hand of the chromatogram. It's called, it shows the retention time of each measured component in seconds. So then if you look back on the chromatogram, the retention time is shown on the x-axis in seconds. So if we look at the one that highlighted, this is the H2S. The elution time, it is telling you should look at about, okay, I can't see with my glasses. So it's 154 seconds. So then if you look at the left hand, you'll find the 154 seconds, that little peak in the middle, that's the H2S peak. So that's how you determine which peak is for which component, depending on the retention time. Retention time is the time from the sample being injected to the time when that component elutes from the detector. So the way to determine the concentration of each component is the area under the peak. It is integrated mathematically by the software. But of course, we don't need to do that calculation ourselves. The GC will just spit out the result, right? So let's see how well the GC performs for this application. For GC, we measure the performance by repeatability. And the table on the top, on the right hand, defines the allowable limit of each component. It's for 8 hours ambient temperature run, continuous run for 8 hours. You take all the readings. So for each component, we set the allowable limit. The allowable limit is maximum value, and the difference between the maximum value and the minimal value divided by 2. That's how we know the plus minus repeatability, right? So the table on the low right hand shows the actual value we recorded during that 8 hours run. So I'm just going to pick 2 components to see, okay? For the H2S on the top, we set the allowable limit is 0.02%. Remember the range is 100 ppm to 2%, right? So now look down, we see the actual result. After the 8 hours run, we recorded the variance was 0.002. The range is 0.02, so it's 10 times smaller than the limit. So obviously it passed, right? So let's look at the C1, methane. That's the key component in the raw gas. The range we set on the top is, the range is 0 to 100%. The allowable limit is 0.35%, more percent. And the actual result, you look down, C1, after 8 hours run, the variance is 0.027, very small. So it also passed, well within the allowable limit. So on so forth. Each component or each value being measured or calculated, they all pass the 8 hours repeatability allowable limit. So it was a successful application. So the next application I'm showing is for measuring the biomethane. That's on the product side. So we know that the biomethane has to meet the pipeline quality standard before it is being injected, because we have to make sure it meets the spec. So we are all familiar with the natural gas pipeline quality standard, where the measurement typically is C1 to C6 plus, BTU of course, and then CO2, nitrogen, H2S. And on the product side, we know that the H2S level is much, much lower, right? It's usually it's a single-digit ppm. For this application, the sample we tested, the H2S range is 3 to 30 ppm. So you can see all the ranges for the other components, methane all the way to C6+. It's quite typical for natural gas pipeline. So for this application, we used a Model 700XA GCs. It also has one sample stream and one calibration stream. Due to the low ppm H2S measurement, all the wetted tubing are silicone coated to make sure that the H2S molecule does not stick to the wall, right? So then the analytical valve, diaphragm valves, you can use helium or other inert gas to do valve actuation. And the stream switching is automatic by internal single block. Helium, okay, and the measurement, okay, 2 thermal conductivity detectors are used for this application that directly leads to the very short cycle time, that's 3 minutes per stream. So you look at that on the left, we are measuring more components here, right? But because we use 2 TCD detectors, the measurement cycle time is shorter. It's only 3 minutes per cycle. So then for this application, you can use helium or hydrogen as carrier gas, and the system power is now 85 to 240 VAC. So this is the measurement result. And now we see on the chromatogram, there are 2 chromatograms. And for each TCD, it has a dedicated chromatogram for it. The one in blue is the TCD that used for the C6 measurement. So you can see all the peaks for those components. The other chromatogram in red is dedicated to H2S measurement. So if you look at the elution, the retention time table on the right, the H2S is highlighted on the bottom. I can't read the number, but you look at the elution time, the seconds, then you go to the left, you find the peak. The H2S peak is that little peak in the center, the red one, because the level being measured is very low, right? Only 3 to 30 ppm. The peak is very small. So then the same thing we did, we run 8 hours ambient temperature, the repeatability test. We set up all the allowable variance range for each component. So then we take recorded the result for those 8 hours run, and we compare the actual variance against the allowable limit. If it is within the limit, pass. If it's out of the limit, fail. Then you have to start another 8 hours continuous run. The only way to pass is each component are well within the allowable limit. So this is another successful example using GC to measure biomethane. So from these 2 examples, we can conclude for biogas measurement, what are the customer needs? Customer need that one analyzer can measure as many components as possible. The reason we know the financial driver for the RNG or biogas is really mainly the government mandate, regulations, or subsidies, right? For the producers to make profit, the cost control is crucial. So they need analyzer that's cost effective, can measure as many components as possible. And the analyzer has to provide accurate measurement because you are trading the biomethane as a commodity. GC is part of the cash register. You have to make sure it's accurate. And the GC have to work online, provide measurement in a timely manner. Also, the analyzer is very commonly installed outdoor in harsh environment. So I always believe the best technology is not the fanciest one, is the one that meets all customers' needs, right? So for this instance, for biogas measurement, GC is the best technology because one GC can measure comprehensive composition. It provides both the BTU and the impurity in one analyzer. And because of its technology, the inherent accuracy, it separates the component. There's no interference. Online GCs work online 24/7, never rest. And the measurement cycle in minutes meets the requirement. And also GCs are very rugged. You can use them in harsh environment for very, very long time Because of this, GC is the best suitable technology for biogas measurement. So the conclusion is, by choosing the right model of the GC for your biogas applications, you can achieve high product quality and safe production and transportation. So that's what I have for you. Thank you very much for your time. I think we, thank you. Thank you. So we have a few minutes for questions.
Are there any questions?
Yep.
It is early, I know.
No, there are. You're there?
Okay.
Yeah. People. Okay. Oh.
Sorry, it's early. My legs are not moving fast this morning. Who was here?
Thanks for the great presentation, Alice. Would you be able to share with us, you indicated in your summary there the customer needs, but perhaps you would be able to share what the biggest challenge is for a GC in those applications?
So for biogas measurement, because it's so similar with traditional natural gas measurement, which GC has been so commonly used, really no real challenge. The only thing I would say, not a challenge, is that typically in those biogas, especially in the raw gas, there's always high moisture content, H2O. So the sample conditioning system needs to be designed properly to remove that water, right? So GC manufacturers sometimes does not make sample system themselves. So they need to really carefully select those integrator, the partners, to make sure they really understand how to design those sample systems. Yeah.
Yeah, just one quick question. I believe you mentioned that if they didn't want to use helium as a carrier, hydrogen was an option. Did I understand correctly?
So for that specific application I showed, we chose to use helium as carrier gas. But if customers prefer to use hydrogen, we can configure it that way. Thank you.
I think we have one more over here. You guys are going to have to clump it together instead of having me walk all the way across the hall twice. I'm old.
Hi. Thank you for the presentation. And how do you demonstrate compliance to the EPA regulations for the biogas GC?
Okay, so what I meant is that for biogas, raw gas, EPA requires that the producers have to at least give a measurement update every 15 minutes. It's not like a certification process, it's just a requirement. And that application is designed to do the measurement in 5 minutes per cycle. So basically you can measure 3 cycles in that 15 minutes window.
Actually, you do have a compliance requirement. You have to meet the ASTM 7164. Otherwise, they won't accept it.
Yeah, I think I'm just talking about cycle time, but yes, we do understand there are requirements to be compliant, which is not the scope of this paper. Thank you.
And how do you handle the moisture in the biogas?
Yeah, so like we just mentioned, the sample system has to be carefully designed to make sure you remove those moisture. And depending on the manufacturer, each GC have different levels of moisture tolerance. So you have to work with each manufacturer to understand and make sure your sample is dried that can meet the analyzer's requirement. The GC does not measure moisture, if that's what you're asking for.
Okay. If there's any other questions,
I will be at the booth downstairs. Feel free to come to chat with me.
there you go.
Thank you very much. 谢谢.
Our next presenter is Elena Hagemann.
Hagemann, yes.
Okay. And Elena is going to be talking about streamlined refined fuel qualifications with process Raman spectroscopy, which I know a lot of people are interested in. Elena is a seasoned expert in process spectroscopy, currently serving as the product manager for process spectroscopy at Metrome, USA. With a career at Metrome spanning over a decade, she has progressed through roles including spectroscopy R&D intern, spectroscopy application specialist, and spectroscopy production specialist. A full range of the manufacturers in spectroscopy. Elaine holds a Master of Science in Analytical and Bioanalytical Chemistry from Elion?
Aalen in Germany.
Aalen, I'm sorry. She can correct me on all my mispronunciation. And a Bachelor of Science in Forensic Science from Bonn, Rhein-Stag University of Applied Sciences. Thank you for joining us.
Thank you
Elena.
for the opportunity to speak this morning. First of all, I really appreciate the time that I can present process spectroscopy. It's probably well known to some of you and brand new to some others. So I hope that in this presentation you get something, even if you already know process spectroscopy. And since we are in Galveston, beautiful Texas, my presentation is around gasoline applications, but the principles that I present can also be applied to solvents, chemicals, polymers, food and food industry. Spectroscopy is not specific to a product, an application, or an industry field.
Get close to the microphone.
Yeah, I just realized that.
Our technology people back there said that they can't hear us.
Well, then I talk directly into the microphone and hope you can hear me
Either
better.
that or you can use this one.
Process spectroscopy is not specific to an industry field, an application, or a product type, so the principles that I present can be applied to other applications as well. And so the content of my presentation, I have a slide on industry trends and needs. I want to refresh your knowledge on Raman and PAT, and then I have examples on identification of various hydrocarbon samples, and we want to go into quantification of fuel blending using process Raman technology. And then I want to emphasize the use of ASTM methods to successfully implement spectroscopy, because there is always the little bit the worries about how do I bring this technology to life? We talk about chemometrics, and that's not always a topic everyone is aware of. So what are the industry trends and needs? Wherever I go, all your websites says sustainability, efficiency, innovation. So we as instrument vendors want to, of course, help you to achieve those goals. And behind this is usually the goal to optimize your production and to increase the quality of your product. And by using tools that monitor while things are happening, when you do not rely on end product testing, you ensure that the product that you're producing actually is of higher quality, rather than waiting until something is produced and then you realize it's off spec, and then how do you deal with that situation? So monitoring of what is happening is very important. And those instruments that you use to monitor your production should be instruments that are easily installed and probably run 24/7 on their own and don't need a lot of user interaction, because shutting down your production usually means you cannot produce, and that equals money. So it needs to be quickly implemented and run by itself. And we also see trends that everything goes towards data analysis, using more data of your product to make smart decisions, or even let software make smart decisions for you. And by using PAT tools like process spectroscopy and be compliant with ASTM methods, that's kind of what we want to achieve, and that will bring you closer to your goals. Common challenges that you have probably with your common testing methods is manual sampling, if you still do analysis in the lab environment where you grab a sample, bring it to the lab, run multiple technologies on these samples. Each technology takes 20 minutes, 30 minutes, an hour, and based on those results that get transferred back to the process, you make your decisions. And during that time, an hour or two, production already continued, so the response time is just delayed. And also, whenever you have operators involved that need to handle solvents, that need to grab samples, that need to run some technology, there is always a safety risk as well. And so, process spectroscopy does not need to deal with these challenges. Just a brief reminder on what is Raman spectroscopy in case you have not worked with spectroscopy before. It's a vibrational spectroscopy technique. It's kind of a molecular fingerprint. It's specific to the substance that you are analyzing. And the way it works is you shine a laser of a specific wavelength onto your sample, and most of those photons, they will be elastically scattered. That's Rayleigh scattering. We don't care about those, but a small portion of those photons are inelastically scattered. That's our Raman scattering. And this energy shift reveals a lot of information about the molecular bonds and the structure of your sample. So by shining laser light on your sample, we create a spectrum, and the spectrum can be analyzed in various ways like identification and quantification. This will be my examples later. So what are the advantages of the technology? Non-destructive. You can place a probe, a flow cell into the production exactly where you want to take a measurement. It's quick. We speak about milliseconds to seconds depending on your sample type. There's no delay in response or anything. It's very specific to the sample that you're analyzing, and also you get various results in the same time. If we speak fuel blending, I think the list is 15 or 20 different parameters, different aromatics contents. You have your octane, your Raman, all these things can be analyzed in the same millisecond scan, and you don't need these various other technologies to get the same results. So it kind of makes it a perfect tool for process monitoring. And just a refresher on process analytical technology, all that we do with those process analyzers, we really design systems that allow you to analyze, control, monitor what is happening in your production in real time, and then in real time be able to make decisions based on those results. The examples or the topics that I want to address in this talk are two. One is everything around raw material, feedstock control, storage, distribution. And again, my example is fuels or gasoline, but you can imagine everywhere where you have chemicals stored, delivered, you don't want to mix chemicals that could, for example, create chlorine gas. You don't want to mix raw materials of similar grade and then you produce something with a raw material that doesn't have the right specifications. If you pump products through pipelines, you want to ensure that the time where you have transmix of different products is minimized, or if you have cleaning cycles where you pump things through pipes, you don't want to waste a lot of product. You only want to waste the product where there is transmix. And then the other example will be around quantitative analysis, process monitoring and optimization of various parameters for fuel blending. The analyzer that we use, or the experimental setup, is a small Raman sensor, and it's about this size that you can directly plug into a reactor, a pipeline, or a storage tank. And the front portion that you see is customizable. So if you use a different kind of flange or clamp or whatever, then that front part would be changed. The Raman sensor has a 785 excitation wavelengths. That's useful for most applications. Sometimes the laser would need to be changed, and this instrument is self-calibrating, so there's no need to put a calibration standard or anything onto the analyzer. It's self-calibrating. And then the samples that we used for this experiment are diesel, jet fuel, and 2 grades of gasoline. We collected spectral data at room temperature, so this is the feasibility study. Can the analyzer be used to do this application? Usually we would look into temperature, pressure, influences as well, but the first question is, can we do it or can we not do it? And that's typically things that we do for customers, do those feasibility studies, because spectroscopy is mostly new, and then people want to understand, can you actually do it? There's not thousands of papers like for other technologies available. And so we collected spectral data, and the analyzer takes a dark measurement first, so that's collecting the baseline noise of the instrument to correct spectral data. And then acquisition parameters get optimized so that you get the highest signal intensity and the best signal to noise ratio, which is especially important if your component is not very Raman active. That's when you really have to fine tune and ensure that you get a good spectrum. And then the analyzer, as I mentioned, is self-calibrating, so before every scan it does a quick internal scan to ensure that peak positions and such is still in place. And here's just an overlay. Oh, I hope that you can see light blue. It was probably not smart to choose light blue, but this is the overlay of diesel and jet fuel, 2 different product types. So we were expecting that there are regions where we see a difference in the spectrum, and that's around 400 to 600 wave number. That's the region that can be used to distinguish between those 2 products. If we look into an overlay of the 2 different gasoline blends with 10% and 5% ethanol, the spectral shape becomes more similar. There is some intensity variation, but there are still regions in the spectrum around 700, 800 wave number where there is a difference in the spectrum. And so during method development, we would focus on those regions where there is a difference in the spectrum to build a library. And we threw those data into a principal component analysis. That analysis just shows us that we can classify those 4 different product types. They are distinguishable, and that's a proof that we can build a library on those 4 different components. Since 4 is probably not very impressive, we just added 9 other hydrocarbon samples like xylenes, toluene, isocyanate, octane, heptane, hexane, pentane into this library. Did the same thing, scanned, next slide, send in 10 independent samples per product, applied data pretreatment, which again is very important or very commonly used in spectroscopy just to get rid of like baseline shifts, fluorescence. If there are some shoulders overlapping information, then data pretreatment would make that more prominent into the spectrum. And then the regions that are showed on the slides, we use those to build the library. And then once a library is developed, it needs to be validated and then transferred to the analyzer. And how does this analyzer now work that we built a library and saved it on this instrument? Again, it doesn't have to be a truck, it can be a ship, it can be a pipeline that transports a product or different products. In this example, a truck delivers a new chemical. The operator would walk up to the interface and says, hey, I'm unloading gasoline, and this activates a scan on the little sensor. It takes a couple milliseconds. It compares this new scan with the library on the analyzer, and if it passes, it gives a pass result to your control room, your SCADA system, whatever you are using, and it automatically opens a valve and allows the product to flow into a storage tank. And of course, those libraries need to be developed. They need to be developed for the products that you expect to be delivered or run through those pipelines. But once the application is developed, then you can use the analyzer on new samples. I have this slide on how the software operates, because we do not want to rely only on that one passing result. So there's programming behind where you can build an average on 10 scans, or use 3 times passing results before you're allowed to open the valve. So all of that can be programmed and customized depending on your setup. When I submitted the paper, there was right away the question, well, it's great that you can do that on raw products or on clean products, but what about transmix? When things are mixed in a pipeline, they don't perfectly behave one product after the other. They start to mix when they run through pipelines. That's the typical downgrade of your product. It could also be if you run a cleaning cycle, right? Then you have your good product, you run a cleaning cycle, you have a situation where it is mixed, and at one point you have product again, and you do not want to throw out a lot of good product because you're not so sure how long is there actually cleaning solution in your pipeline, or when is it actually switched to the next product. So you can imagine the analyzer measures in real time what is actually happening in your pipeline. And so we did some initial scans, and again, I have to apologize for those colors. We can look later at this at the graphics again if you would like to. But there are regions in the spectrum that are specific for diesel. There are regions in the spectrum that are specific for gasoline. And then we looked into 0.5 to 3% diesel in gasoline and see that there is an increase of that diesel-specific bands with increasing concentration of diesel in gasoline. And we did a similar experiment for premium and regular, where we distinguish between those two first, and then what happens if they are mixed. Is there a difference in the spectrum? And the answer is yes. It's initial studies, so it is ongoing. We are still collecting more data, but the first scans of this look very promising. Then I also mentioned that we can do quantitative analysis with Raman spectroscopy as well. So various parameters in petrochemical industry, in this fuel blending like RVP, Raman, distillation points, aromatics content, all of those parameters can be analyzed with process spectroscopy as well. And I mentioned that it's especially important for this secondary technology to follow some guidelines that help you with the implementation. And the ASTM methods that I want to mention is D8470. And again, it's not specific. It is developed for petrochemical products, but using what is written in those ASTM methods help you in any other industry field, because it's proven in those methods what you need to do to make it a success. So D8470 is all about what does the spectrograph, the spectrometer require, the calibration of the analyzer, the standards to ensure that the instrument is always performing according to specifications. Then there are, of course, methods around the secondary and the primary technologies, or your octane engines, the titrations. There are methods around that. But then D8321 covers quantitative method development. So if you have good spectral data and you have your reliable reference values, how do you bring them together using chemometrics to do a quantitative analysis? And then in D6122, it talks about validation, because you do not only develop those methods, you also have to prove that they are valid, apply them onto new data, create some outlier statistics and some statistical values around the validation. And what is new, and that allows you to use spectroscopy also for product release, is what is implemented in D8340. It talks about the results validation. So once the analyzer is calibrated, has those methods installed and run in routine, you want to ensure that the predicted results or the spectral data still fit to the data that you use during model development and validation. So it's a continuous check of your method. And by following those methods, you can be very sure that spectroscopy can be implemented successfully. If we lack in one of those, then it takes longer and it's more challenging to implement it. As I already mentioned, those the ASTM methods help you in the different steps. And how does application development for spectroscopy work? You scan all your sample, or the quantitative application development, sorry, my mistake there. The quantitative application development means you scan your data, the samples need to cover the range of interest, either around your target, but a little bit outside of the target region as well. And then you run those samples on your primary test method. So if you currently do a titration chromatography or something else, you scan those samples on your primary test method as well. And then you have two data sets, spectra and reference values, and use those during model development to make spectroscopy smart. It cannot do anything besides giving you a spectrum. And then when the analyzer is calibrated, it goes into routine operation and is independent from the reference technology. Once in a while, you still run a check sample on your reference technology to ensure your method is still working, but it frees your laboratories, your operators, your instrumentation to probably run some other analytical questions, and you do your monitoring on spectroscopy, and can still do the final product testing on primary testing methods. Then, as I mentioned, there are ASTMs that give you or gives you a long list of calculated physical and chemical parameters that are allowed to be analyzed using spectroscopy. And what we did, we collected spectra of various origins. So this is not only one gasoline sample measured 10 times, I think, or 15 times. It is gasoline of the same grade from various origins. And you see that there is already some spectral variation just dependent from where the gasoline comes. Applying pre-treatments help us to summarize these data to make them more valuable to the quantitative analysis. Here's E10, just a different data set. I'm running a little bit out of time, but what I want to show you, we have data collected for like distillation temperature, the D10, D90 on gasoline or E10. We've done that for vapor-liquid ratio temperature on gasoline and the E10. We've done that for relative density, we have that for ethanol. Actually, the water content data is NIR, but we've collected a lot of spectral data for those quantitative applications. And what is important with spectroscopy, if you look at those correlation plots, is maybe like you're used to perfect dots on a line. If we think about like chromatography or something, in spectroscopy, it is more important how well does it predict in the end. We have to capture variation, and that's why the data turns a little bit more into clouds than perfect aligned dots, but capturing variation helps us to build robust models. And then those models can be applied on this data. You remember when I overlaid spectra and there's a lot of variation, that needs to be captured to make it then robust. And then we look more into prediction errors, calibration errors, and if they are small, then we know it is a model that predicts well. It is not that we have to have the perfect aligned data points on a line. We also did MON, RON, AKI on octane samples. There's just a lot of various quantitative models. And I wanted to just go to the benefits because I'm running a little bit out of time. But what I want to summarize with this presentation is that you usually have a certain interval when you analyze your product, and you have to react to those results. If we have spectroscopy implemented, which runs much quicker and is directly implemented into your process, you increase your measuring frequency and you can react to changes much quicker and therefore produce closer to target. And in this example, we were looking into RON and MON, and in gray we see our offline measurements, the octane engine. It takes a while to get those results, and then in green we have inline spectroscopy measurement, higher frequency, we can react closer to it, and we have our, in orange, our target line. I think that was 87, no, maybe it was, I don't remember, 93 as a target range. And so you don't give away octane if you are producing or you're blending closer to target, and do not wait for the octane agent to give you back the results. And with that, I am through a lot of various topics, and it's probably now like, how do I apply that to the things that I am actually doing? It is difficult since spectroscopy can do so much. As long as there is a reference technology in place, there is the way to move that to spectroscopy as well. There are a few limitations, but a lot of things can be done with process spectroscopy. And I would be happy to take some questions or have you stop by the booth later and talk about your specific situation.
You have to raise your hand if you have a question. I have a question. What do you do about outliers?
What I do about outliers?
Uh-huh.
Yes.
I saw your graphs, and you had a lot there. But were the red dots outliers of
Yeah,
the
so
spectrum?
if there are outliers detected, and that's why I mentioned ASTM methods, there are hot-link t-square, Q residuals, nearest neighborhood, so the statistics in the software indicates the sample to be an outlier not fitting to the data set. And then it's the question either to retest them on a different technology to ensure it fits to the data set, or it's probably incorrectly measured, or it's a true outlier. So then they would be excluded.
Yeah, just a quick question. One of the things I recall about Raman is the really fast analysis, even if you co-add spectra. What's the typical update time between updates on the measurements?
So, I mean, each individual measurement is just a couple of milliseconds, and even if you would average, it's just a couple of seconds. Or maybe I didn't understand. Okay, no, it's milliseconds per scan, and even if you average them, it's still a very fast measurement.
Hi, Elena, great talk. So in the first part of your presentation, you shared the raw material library qualification. How does your software handle completely new or foreign raw materials that are not contained in the library? Do you get a non-match, or does it just give you a prediction of what is closest raw material to the new material?
So if it is not in the library, it will be seen as an unknown. It doesn't give you a pass or a fail, it just will indicate it's not in the library, and you can program all kinds of alerts into the software. If you want to be informed that it's new and it's not been in the library, then this information will be displayed in your SCADA system. So it's an open software what to program there. But if it doesn't know it, then it doesn't know it and doesn't give you. It could be because we really want to verify it is the product that we expect it to be. It's not an unknown identification. It could be set up that way. It's probably more handheld or benchtop Raman, but this sensor type is for, is it the product, yes or no?
Good morning, excellent presentation. I have a question about diagnostic information. Can you elaborate what kind of diagnostic information can help you to determine the quality of the data?
I'm not so sure if I got that correctly. So diagnostics on the hardware or the diagnostics of the results?
Yeah, from the analyzer itself. I can imagine.
From the analyzer itself, so what we have on our instrumentation would be internal standards. So we know defined peak positions, and then there's an internal reference channel that measures this known standard and compares it to the known peak positions, and the same for intensity as well. It has a defined intensity for that standard, and if we measure the standard, it has to reach a certain intensity. That is done before every sample scan. It checks it. And then if we think about diagnostic tests, like running a performance test, for example, would be a similar setup. It runs the internal standard and ensures that peak positions, nothing has drifted over time. Laser intensity is still the same.
Okay, thank you very much.
Thank you.
Okay, I'm going to remind everyone that we have a very special day on Thursday afternoon before the awards, and that is that we are going to be giving Merriman a Lifetime Achievement Award. And he doesn't know about this, but we have his whole family coming in off that elevator, coming in the backside, and it's going to be a very special time. So please, if you can make it Thursday at 3 o'clock, then please be here, because that will be Del Merriman. We will be honoring him for the 45 years he's put into the analytical business. And a lot of you guys know him. So anyway, our next presenter, sorry, let me get you over here. Chuck DeCarlo. He is from Process Insights. He's the Director of Global Applications, and he has a Bachelor of Science of Biology from Allegheny College, Meadville, Pennsylvania. That's kind of God's country, people. Anyway, his work history is, he has a career in process analyzers beginning 18 years ago with Extrel mass spectrometers. Over the years, he's done field service, product management, marketing, sales, and application, primarily working in the process control, safety, and compliance area. With Extrel's acquisition by Process Insights several years ago, Chuck now manages applications for a wide range of industrial analytical technologies, including mass spec, NIR, FTIR, UV, Viz, colorimeters, total sulfur, and oxygen analysis. His hobbies are hunting, fishing, camping, and coming to ATC. That's not here. I'm just mentioning that.
It's a big hobby. I love it.
It's a big hobby. Welcome, Chuck.
Thank you.
And clicker's right there.
Oh,
Do you
wonderful.
want to use this, or do you want to use the microphone?
Yeah, we'll give it a go.
Up to you, either one.
Okay. Thank you very much, Wes. I appreciate it. Yeah, and also I wanted to say thank you to Phil Harris, my co-author on the paper, and thank you to all of you who are joining us this morning. I figured with it being the second day of the technical program, and at this point, all of you have sat through lots of very in-depth, very highly technical presentations. I wanted to start with something that we all love, something that's a lot of fun. And so I thought, what would that be? And I came up with taxes. I thought filing for taxes, something we all love very much. And actually, thanks to the way that our governments in the US and Canada and elsewhere have structured the regulations, our customers now, when they think about carbon capture, they're thinking about taxes, right? And they're thinking about the tax credits that go along with them. And so, this becomes an interesting situation, right? Whenever we have an application, right, in the analytical world that involves regulation, we suddenly find that we get new ways to think about how our efforts impact the process and impact the lives of our customers. And because everything's written down in the laws itself, we actually can now see some of that return on investment. And we can see kind of directly how the performance of our analyzers and the performance of our analyzer programs impact the day-to-day life of our customers out there in industry. And so, that's really the game that we're going to play here this morning. We're going to be like the analyzer version of H&R Block. And I'm going to look in general at analyzers that are used in carbon capture, but also at a specific project that we currently have going on up in Alberta. And we're going to look specifically at mass spectrometers and cavity ring down analyzers that are being used in the CO2 quality measurement and how that impacts not only the day-to-day operation of the carbon capture facility and the pipeline, but also the financial impact all the way through to the tax credit. So, okay. Starting at the beginning, why are people out there doing carbon capture? I mean, we see this a lot in the news, and in fact, in the technical program this year for ATC, there's several papers on carbon capture. And it's an exciting topic because it's fairly new. Not only is it fairly new, but you talk to what folks out there in industry are doing, and there's a wide variety of technologies that are being applied, not only on the capture side, but also from the analyzer standpoint, of interest to all of us ATC people. Also, we've got, as I said, right, these tax credits, which means there's a direct financial benefit to those customers that are out there doing these things. Now, of course, the goal is an environmental goal, right? And going back to a series of international treaties, including the Paris Agreement, there is a drive internationally to reduce the impact of carbon emissions as much as possible. And so, we see things, metrics like the, international targets to, increase carbon capture by as much as 840 million metric tons by the year 2030. According to the International Energy Agency, that's a 20-fold increase, from where we stand today. So these are all extremely aggressive targets, and we see a lot of movement in industry as a result of that. And some people have asked me about, what impact the political climate, might have on that. And of course, things are always subject to change, but again, these are international targets, and so some of that kind of levels out when we look across the globe of what's going on. Overall, we know that there's a lot of work being done. Carbon capture is an important part of the overall plan to reduce emissions, because at the same time that governments are out there pushing for industry to reduce the CO2 that's being released, life has to go on, right? And we need energy, and we need chemicals. And so carbon capture is one of the technologies that allows industry to continue to do what they need to do to supply all of us with the things that we need for daily life, but still reduce the overall CO2 emissions. So for that reason, right, we get governments that are putting in place incentives. And those incentives are the tax credits that I referenced. So here in the US, the IRS code has the 45Q tax credit written in specifically to allow industry that is capturing and storing carbon to offset some of the costs of putting those processes in place. Okay, so this is the government showing up in the words of Ronald Reagan saying, "I'm from the government and I'm here to help." And so how are they going to do that? What you see is the tax credit is determined by the type of industry that's being, the type of industry that they're dealing with. So this includes chemical plants, oil refineries, steel mills, power plants. So you can see that's the first row on the chart. There's also direct air capture facilities. So that's technology that's pulling CO2 right out of the air. They're also subject to the credit. It also then is determined by what the ultimate use of that carbon is going to be. So a lot of captured carbon goes into permanent storage in saline aquifers. Other captured CO2 gets, sent into the pipeline and taken over to other chemical plants where it can be used to produce farther goods, right? It can be made to make chemicals. Or that pipeline takes it to oil fields and it's used for enhanced extraction, and it's pumped back underground for oil drilling. And the tax credit is determined by those two factors, so where the carbon comes from and where the carbon is going. And you can see that it's paid out as a function of the metric tonnage of CO2 that is being captured. Okay, so the IRS says, tell us how much CO2 you're capturing, but now it falls on the back of the EPA regulations to tell us how to do that. And I'm not going to go through a major digest of the EPA rules, but in the greenhouse gas reporting regulations, you see a number of calculations very similar to this one. This one comes from subpart RR of part 98. And it describes the very specific case for, if you are measuring the flow of your CO2 with mass flow meters, and, if you are setting it to underground storage. So they've got different equations based on, kind of how you're doing your measurements and based on where the CO2 is coming from and where it's going. But this is a good representative version of what the equation looks like. And what I want to point out here is that according to, in this case, US EPA, the calculation for your actual carbon reporting is pretty simple. Right? So everything here is based on quarterly numbers, but what you can see, the real parameters that go into the calculation are simply the flow of carbon that you have coming in, the flow of carbon that you are not sequestering. So, if you're setting this farther down the pipeline, for example, and it's all just multiplied by, here we go, the concentration of the CO2 itself. So we're talking about a very simplistic equation. Quarters add up, and you get your annual, tons of CO2 that are captured. Okay, so you got input from flow meters, and you've got input from the analytical. And so right away, we can start to see where this direct economic impact comes into play from our CO2 quality analysis. Okay, so right there is an interesting point for trying to design our analyzer program to ensure that we maximize the quality of that measurement. Now, that's not the only reason, of course, that your carbon capture plant needs to make measurements. So this is still a chemical plant, and therefore it's subject to the same kind of control considerations, quality, longevity of equipment, all of the same things that our customers have always cared about apply when we're looking at the carbon capture process. And so here, I know this diagram's a bit busy. There's a lot of things squeezed in, but you can see kind of the three main approaches that are currently being deployed for carbon capture. So the idea, of course, is they want to make sure that CO2 emissions aren't being released. Well, there's a couple of times that there's a couple of different ways you can go out and capture that carbon. Most sites are doing, a post-combustion carbon capture. And so that's the top row. You can see that they're going to be manufacturing or they're going to be running combustion, and they're going to take the off gas of that and they're going to desulfurize it. I don't know if you can see the laser pointer's a little bit weak, but they're going to desulfurize it before sending it into the carbon capture cycle. Now, people use phase separation. They use selective membranes that do the carbon capture. But the most common approach out there is actually using an absorber column. And they're going to use ammonia or MEA or another amine to go in and strip the carbon out of the emissions stream. And so that's what I've got pictured here, is the absorber column. And then they're going to take the rich absorber in, and they're going to strip it. So they're going to hit it with steam, and they're going to pull the absorber and the CO2 out of that loop. Now, if they're doing this post-combustion, right, it's all happening after the main manufacturing occurred. There's also sites that deploy a pre-combustion technology where they're essentially gasifying the feedstock so that they can take the carbon oxides out of that and then use the hydrogen downstream for their fuel source. And the third type you see along the bottom is called an oxy-fuel combustion. And basically, they're just using an ASU to generate a pure oxygen stream, and they're doing their combustion in excess oxygen. And so in that case, the combustion byproducts are basically pure CO2 and water. So they don't have, the nitrogen compounds to deal with. So they just get a pure CO2. In all cases, right, the last step typically is going to be compression, because you've now got your captured CO2 and you got to do something with it, right? So what we see is this paradigm where you've got your chemical plant or your power plant, right? You then have that connected right to the pipeline, which is going to take that to their customers that are either using that CO2 for oil recovery, or they're taking it and they're pumping it down underground. Okay, so pipeline transportation, on the diagram, these are really short lines, but that's a major part of this process. And it really determines a lot of the considerations that we put into how we do the analysis and what kind of purity matters for the CO2 that's being captured. So one thing I'll highlight is, of course, since this is ATC and we care about, analysis along every stage of these processes. We really care about how they're running these plants. The CO2 quality measurement is not the only measurement that's going on at carbon capture facilities and the associated production sites. So, I'm going to focus in on CO2 quality for the sake of thinking through how that impacts tax credits, for example. But, these are combustion processes. So, these sites need, combustion analyzers, at the power plants or, for people that are generating steam. There are process control points for, multi-stage processes, whether it's, the gasification at a pre-combustion removal site or, whether it's, just the plant itself. Water quality analysis, again, we're talking typically about a lot of steam, and of course, the CO2 measurement. Now, a good model for how we can think about the CO2 measurement is that in a lot of ways, it's a custody transfer measurement. So they're measuring this before it goes into the pipeline. The site wants to know, it's the cash register, right? The site wants to know how much CO2 they're supplying. Pipeline needs to know how much CO2 they're receiving. And of course, it's a quality measurement. The pipeline cares about what's coming in, right? And if the CO2 that's coming in is off spec, it's going to be dangerous to the equipment of the pipeline, they want to be able to shut that plant in. So these measurements are occurring certainly before the CO2 goes into the pipeline, but then, periodically downstream of that as well. Lastly, we know in this case, there's measurements of the final quality before it goes underground. Okay, and so what kind of things do people care about? Well, within the pipeline, if you have excess water, if you have H2S, if you have oxygen, of course these things are going to lead to corrosion, wear down the life of the pipeline. In the case of the project that we're talking about specifically today, their primary use for the CO2 is going to be, for oil recovery. And so, in addition to kind of your standard pipeline considerations, one of the critical factors they're concerned about is the potential for breakthrough coming out of the capture process. So they're concerned about the presence of amines, they're concerned about the presence of glycol, so the glycol that's used to dry the CO2 coming out of the final stripper column, because they're concerned about what impact that glycol might have on the porosity of the material, right, underground where they're doing their oil recovery. So it is an important thing when we approach a carbon capture process to understand, what the driving considerations are for each of those measurements, because it can differ. It can differ based on where the carbon's coming from, and it can differ on what the customer wants to do with it. Okay, in general, though, we can think about the common measurements that get made. And in this case, I took a a couple of combined projects, and I kind of threw everything against the wall in terms of the measurements that we get asked to do in the carbon capture CO2 purity measurement. So naturally, you're going to have high-level CO2. You're going to have your standard usual suspects, water, hydrogen, nitrogen, argon, methane. And you can see that the typical concentration of these components drops down pretty quick, right? I mean, it is a purity stream. But then within the ppm constituents, you get a mixture of sulfurs, especially if this is coming from a combustion process, coming from a stack. You get hydrocarbons, alcohols, the glycol that I mentioned, and various amines that are used as the stripper components. So typically those are what we see. We've had some situations where people ask for some acids as well, like HCl, trace level. And what we find is the sites will go at these with a variety of different technologies. So people can use GCs, they can use FTIRs, they can use NIR analyzers to make these measurements. Of course, I'm going to focus in on the mass spectrometer and the CRDS that we're using in this specific project and talk about some of the reasons why. But yeah, carbon capture is kind of the Wild West right now. And so you see a lot of different approaches deployed, which is interesting. Now, for the mass spectrometer that we're talking about here, all of us with, our rich and varied analytical backgrounds, we might think about, a GCMS or something like that. This is not that kind of a mass spectrometer, right? This is an industrial process mass spectrometer. In this case, it's a quadrupole mass spec that our company, Process Insights, sells. But it was developed for doing real-time analysis. So this is a mass spec. It doesn't have a GC column in front of it. Instead, it takes the gas directly into the mass spec as the primary analysis technology. And what that allows us to do is a number of things that are actually really beneficial in the CO2 measurement. One is that it gives us the ability to measure a very wide range of concentrations. So direct mass spec can measure compounds from 100%, like your CO2 in the stream, all the way down to the ppm level, like a lot of those impurities. So wide dynamic range makes it good for doing carbon capture. The second thing, which I've already kind of hinted at, right, is that a mass spec as a technology can measure many different components. So there's no class of compounds that is invisible to a mass spectrometer. So if you have a long list of impurities of different chemistries, mass spec's a good generalist technology to use. The third factor, which is also important, and people who are doing pipeline applications like CO2 or even fuel gas, appreciate in the mass spec, is that it does a very fast analysis. So you can take a mass spectrometer and it will measure all of those constituents in the stream in a number of seconds. So on this particular model, we talk about an analysis speed of 0.4 seconds per component. So if you're doing an 8-component method, you're getting an update once every 3 to 4 seconds. If there's an issue with the carbon capture process and you can identify it quickly, right, it could ensure that you prevent that or divert that stream before it hits the pipeline, quality check, and gets you shut out of the pipeline, for example. Or if you're the pipeline, it protects your infrastructure from anything coming from a plant that has a problem. Lastly, yeah, the mass spec as a technology, it's nice. These at this point are, industrially, it's an industrial approach. So it's been designed for ease of use, for long-term stability, and a minimum of required maintenance and consumables. So a mass spec doesn't need to have any carrier gas or any detector gas. So it uses calibration gases, but it's generally light in terms of consumables. Okay, now, in the case of the specific project that I've been talking about up in Alberta along the Alberta carbon trunk line, the mass specs that are being used are measuring as the primary components these that I have listed here, with a couple important exceptions that I'm gonna mention. So you can see these specs that came from the program are listed under the requirement there, and they talk about what needs to be measured and at what levels. Now, next to that, you can see what the load detection limit is for the analyzer in this case. And the load detection limit is sufficiently below the measurement required in all cases except for two important ones. And one is the moisture, the water, here, where the mass spec will not give a good measurement because of interferences and backgrounds. And the second is our CO. And these are going to be important. So we're going to dig into them a bit because they're going to impact the quality of that CO2 measurement. So a lot of times we think, it's hard to measure things at trace levels and easy to measure when it gets up to a high percent. But of course, the closer you get to 100%, the more the quality of your trace measurement impacts that bulk value. So suddenly trying to do 100% CO2, it really matters how well we do the trace stuff. Okay, so for measuring the water in this case, we use a cavity ring down spectroscopy system. In this case, it's made by Process Insights as well. This is the Tiger Optics Spark that measures moisture in CO2. You can see the range is from 550 ppb up to 600 ppm. And just like with the mass spectrometer in this case, one of the very nice things about CRDS is fast measurement, real-time response, and very, very low maintenance. So there's no field calibration or maintenance required on these as long as the sample stream is kept clean. Okay, and here you can actually see the performance of that, measuring 50 ppm moisture in the CO2. You can see it says oxygen on the top of the screen. That's I blame my quality guy for that, who is also me. So that's a bad typo. But yes, this is actually a moisture signal, not an oxygen signal. And so yeah, we're doing this with our CRDS, and then that data is going to be combined with the mass spec. Now, I'm not going to look at a data trend for all of the impurities that the mass spec is measuring. However, I do want to just show some highlighted examples. In this case, this was done as a validity check, kind of in the lab. So we're looking at bottled gases, not real-world captured CO2, and we're challenging it with, in this case, oxygen. And we're measuring, 1,000 ppm of oxygen in pure CO2. And you can see that the response time is very quick. The spikes come up, they clear very quickly. Same thing in this case, looking at methane, another one of the big impurities that we care about. In this case, the repeatability, so for the methane signal, is really high. So we get very high precision. And each of these spikes, the average, plus minus is really plus minus 9 ppm on that signal. And so as I mentioned, the quality of your impurity measurement directly translates into the quality of the CO2 number. And that's what determines the impact on the tax credit. So here you can see, if we look at that equation, RR1 that we had before, where we've got our, how we're calculating the CO2 that's captured. If you take the repeatability of the measurement, in this case, the CO2 measurement, which is plus minus 20 ppm, and you calculate the financial impact that'll have on the tax credit, you can actually drive that uncertainty all the way down into like the $1,700 limit. So in this, example where we're going for ideal repeatability, and driving for the best possible CO2 measurement, you can ensure the highest confidence of your reported CO2 tonnage, and therefore guarantee that you can claim the maximum tax credit. So in all cases, what you want to do is design that analyzer program to make sure that you're maximizing that result. Okay, and I think with that, I'm about at time. So Wes is going to come up and he's going to pull me off stage.
Are there any questions? Just to let you guys know, after the break, we are hoping that there will be 2 microphones, one here and one there, and you will have to get up to go to the microphone. Who was it? Yeah, I don't need all the steps. I have plenty of steps.
Thanks for the presentation. My question, looking at the whole carbon capture systems that you showed, isn't a mass spec a bit of an overkill? Particularly when it seems like you could do the job using, let's say, using a GC, for example. And since you're not using a GC with the mass spec, which means you're not separating the compounds before it goes to a mass spec, then doesn't that make the analysis more complicated because now you have to think about the other signals coming from the other compounds in your stream? So I'd like to know your thoughts on that.
Yeah, sure. So, I mean, first, you can certainly use a GC to do the measurement, and there are those that do. However, there are aspects of any particular carbon capture plant or carbon capture program where they look at it and there are factors that would point them in the direction of a mass spectrometer. And some examples would be the measurement of the amines and the glycols that I talked about, like at ppm level. So, if you can do the measurement with a simple GC configuration, then you're going to have a lower price point on your analyzer relative to the mass spec. But as that measurement gets more complex, if you have to have a TCD and then add an FID as well, now you're adding furnaces and columns, and the cost of that process GC starts to get much closer to the higher cost of the mass spectrometer. In addition to that, if they see benefit in having a faster analysis from the mass spectrometer, so they're getting updates in seconds as opposed to minutes, that can allow them to do a couple of things. Some people will use additional speed to take that analyzer and analyze multiple samples throughout the plant with one system instead of having dedicated analyzers for each sample point. Or they're just using the speed to ensure that they have optimal control, right? Just fresh data that they can respond to very quickly. So typically that's where you see the differentiators between a mass spec and a GC. Second part of your question, in terms of dealing with interferences, direct mass spec as an industrial analytical technique, has been around for many decades. And what you want to do is you just want to work with the vendor for that particular mass spec to ensure that they know what you want to measure, they know how they're going to go after it, and then they'll let you understand, like for example, the water case with the CRDS, anything that you probably don't want to measure with the mass spec, they can help you identify that, and if you need to, then they would design around those interferences.
Any other questions? One comment, if you're going to buy a mass spec and you don't do a data sheet, shame on you. Thank you all, and now you're at break. Thank you.